see the definition. A function fz defined in a domain D is said to be continuous at a point z0 belonging to D. That is your domain. If for every epsilon positive there exists delta positive depending on epsilon and z0 both, right, such that mod of fz minus f of z0 is strictly less than epsilon for mod z minus z0 strictly less than delta. So a function is continuous at the point z0, which is present in the domain, which is belonging to the domain D, if for epsilon positive there exists delta positive depending on epsilon and also the point z0 in such a way that mod of fz minus f of z0 is strictly less than epsilon for mod of z minus z0 strictly less than delta, right? This is the definition for the continuity. Now this is about the function which is continuous at z0, the one point, right? If the function is continuous at every point existing in the domain, if the function is continuous at all the points in the domain, then what would we say? For that there is a remark that if a function is continuous at every point of the domain, then we say that function is said to be continuous in the domain D. If a function is continuous at only one point, let's say z0, then we say that function is continuous at z0. If the function is continuous at all the points belonging to the domain, then we say that the function is continuous in the domain. Alright, let's move on to one theorem which is based on this concept of continuity. The theorem is the function fz that is equal to uxy plus iota vxy is continuous at a point z0 equal to x0 plus iota y0 if and only if uxy and vxy both are continuous at the point x0 y0. Suppose this is your function and this is the domain D, and the point present in this domain D is z0, that is your x0 plus iota y0, right? Now the function is continuous at the point z0 and the function is of the kind uxy plus iota vxy. This is continuous at the point z0 if and only if its real part and the imaginary part, both the parts are continuous at the point z0, right? Its both parts should be continuous at this point. This we need to show. This is the two-way proof. If the function is continuous at a point, then we show that its real and imaginary parts are also continuous at that point. Second way, if the real and imaginary part of a function are continuous at a point z0, then we need to show that function itself is continuous at the point z0. So this is a two-way proof. First, let's suppose that fz is continuous at z0 and we need to show that its real and imaginary parts, that is uxy and vxy, both are continuous at the point z0. This we need to show. Okay, first let's apply the definition of continuity. Fz is continuous at z0. This implies what? By the definition we say that then for every epsilon positive there exists delta positive depending upon both epsilon and the point, that is z0, such that mod of fz minus f of z0 is strictly less than epsilon for mod of z minus z0 strictly less than delta. And now to show that uxy and vxy are continuous at z0. Now from here we know that mod of fz minus f of z0 is strictly less than epsilon, right? So mod of f of z minus f of z0 is strictly less than epsilon. There is also one result that the difference of their real parts and also the difference of their imaginary parts. So mod of the difference of their real parts is always less than equal to mod of f of z minus f of z0. Also, the difference of their imaginary part is also less than equal to mod of f of z minus f of z0, which is further less than epsilon. So from these two, what would we say that? Therefore, mod of uxy minus ux naught y naught, this is strictly less than epsilon, writing this, and mod of vxy minus vx naught y naught, this mod is also strictly less than epsilon. For mod z minus z naught less than delta. So writing this for mod of z minus z naught less than delta, because we have used this. And this is less than epsilon for mod of z minus z naught less than delta by the definition of the continuity of function at the point z naught. So writing this by the definition of the continuity of f of z at z naught. Or you can also write that because it is given that fz is continuous at z naught. Yes, so we have shown that this mod is less than delta for this, which means uxy is continuous at z naught. Similarly, we have also shown that this mod is less than epsilon for again this delta, which means and vxy is also continuous at the point z naught. This is what is needed to be shown for the first part. And now the converse. The converse is these two are given and we need to show that f of z is continuous at z naught. Right? So let's move on to the converse part. The second way. Suppose uxy and vxy are continuous at z naught. Right? And to prove that f of z is continuous at z naught. To show that fz is continuous at z naught, we need to show that mod of f of z minus f of z naught, this should be less than epsilon for mod of z minus z naught less than delta. This we need to show, right? Alright. Now because these two are continuous at z naught, so by definition then, for every epsilon positive, there exists delta positive depending upon both epsilon and the point z naught, such that the mod of uxy minus ux naught y naught is strictly less than, I'm taking here not epsilon but epsilon by 2. It's our choice. Epsilon is a very small positive real number. So I'm taking here this positive real number for this mod, and also for the imaginary part. Let's say the mod of difference of this is also less than epsilon by 2 for mod of xy minus x naught y naught strictly less than delta. This is just a simple definition of the continuity I have applied for the real and imaginary parts of fz for uxy and vxy, right? To show that f of z is continuous, I need to show that this mod is strictly less than epsilon. So to show this, let's evaluate this mod first, putting the value of fz and fz naught. What is fz? It is uxy plus iota vxy. Yes? Minus f of z naught, which is, okay, let me take this in a bracket. Minus writing f of z naught, which is ux naught y naught plus iota vx naught y naught. Very fine. Closing the mod. So this is equal to the mod of, okay, I am separating the real and imaginary parts now. So this is uxy minus ux naught y naught plus iota times vxy minus vx naught y naught. Is it okay? Fine. Alright. Please note that mod of z is what? It is mod of x plus iota y. It is always less than equal to mod of x plus mod of y by triangle's inequality. So I am using this result over here. This is the mod of the real part plus iota times the imaginary part. The mod of real part plus iota times the imaginary part. So this should be less than equal to the mod of real part plus the mod of imaginary part. So this should be less than equal to the mod of real part plus the mod of the imaginary part. I hope it's very clear to you. Yes? Okay. From this result, let me mark this as 1. From 1 we say that this mod is less than epsilon by 2 and this mod is also less than epsilon by 2. So from 1, this mod is less than epsilon by 2 plus this is also less than epsilon by 2, which is epsilon. That means we have shown that the left hand side is strictly less than epsilon, right? So writing this, thus the left hand side, that is f of z minus f of z naught, is strictly less than epsilon, right? For mod of z minus z naught, that is equal to mod of, what is z? It is xy minus z naught is x naught y naught. So this mod is less than delta, right? It is given. So this mod is less than delta. So that is mod of z minus z naught is less than delta. So we have shown that the mod of fz minus f of z naught strictly less than epsilon for mod of z minus z naught less than delta. This is the definition for the continuity of fz at the point z naught. So therefore, f is continuous at the point z naught. So we have shown the result both the way, right? Hence the proof. Okay, thank you. Stay blessed. Have a nice day.